You spend months perfecting a formulation on the bench. The surface energy aligns and the rheology is dialed in. But the moment you scale it up to a 500-gallon reactor, the clear liquid suddenly precipitates into a clouded, unusable solid. Modern chemical engineers possess deep theoretical knowledge. The bottleneck blocking successful industrial production is rarely a lack of basic science. Decades ago, bench chemistry successes relied on far fewer moving parts.
OnlyTRAININGS. Learn what works in the industry.
A chemist could develop a formulation in a controlled, isolated laboratory environment without having to simultaneously solve for global supply chain variations or incoming regulatory bans. An academic understanding of surface energy offers little immediate help when you are standing on an active production line facing a spontaneous adhesion failure. To successfully bring a product to the global market, technical professionals must navigate highly specific, interdependent failure modes, where every variable impacts the rest. For the last 10 years, OnlyTRAININGS has served as the critical infrastructure for the chemical industry, bridging the exact gap between a laboratory concept and a market-ready, compliant product. A technical professional's value in today's industry is determined by their ability to execute theoretical knowledge within the rigid, high-stakes constraints of the real world. The physical reality of an industrial manufacturing plant introduces forces that bench-scale prototypes never experience. The sheer scale of the piping and thermal mass in these tanks instantly invalidates simple theoretical models. A product must survive 3 distinct gauntlets: architectural formulation, process scale-up, and market compliance. We can track a chemical product's lifecycle from initial additive design through to global regulatory submission. This system map breaks down into architecture, process, and compliance. Traditional education treats these phases as isolated subjects. Industrial reality connects them into a tightly woven network. A disruption in your base architecture will send a cascading error straight through to process and compliance. The United States and European markets currently present the highest density of these regulatory and scaling vulnerabilities. Preventing late-stage commercial failure means you have to map and predict these specific technical vulnerabilities before you mix the first pilot batch. Robust industrial design begins at the molecular level through advanced polymer formulation. Meeting aggressive new performance targets in coatings, adhesives, and cosmetics requires highly precise specialty additive system design. But combining multiple specialized ingredients introduces the risk of additive antagonism. This happens when 2 perfectly functional molecules, like a stabilizer and a catalyst, collide and neutralize each other, leaving the surrounding matrix unable to hold its structural properties. Preventing this reaction requires compatibility and stability engineering early in the pipeline. By sequencing integration or engineering molecular barriers, both structures can coexist without destructive interaction. When early prototypes inevitably deviate from theoretical models, R&D chemists must execute rigorous formulation failure analysis. In complex cosmetic and personal care formulations, masking a symptom like separation or clouding will only delay a complete product failure. You have to identify the actual root cause. Resolving these base architectural flaws demands targeted expert intervention rather than broad academic literature reviews. If the molecular baseline is flawed, the entire subsequent scale-up process is compromised. You cannot engineer a base architectural flaw out of a product later on the production floor. Leaving the controlled environment of a laboratory shocks a formulation. When a mixture enters an industrial vat, the variable of thermal mass shifts curing times, viscosity, and chemical reactions, enough to invalidate bench-scale models. Immediate scale-up and process troubleshooting is required to prevent millions of dollars in wasted raw materials during these initial pilot runs. Teams use chemical manufacturing process optimization to balance the necessary throughput speed of the factory with maintaining the structural integrity of the formulation. The product must also undergo thermal and oxidative stability assessments to prove it can survive the friction and heat generated by industrial processing equipment. A successful bench formulation is merely a hypothesis. It only becomes a viable industrial product once it proves it can survive the physical forces of scaled manufacturing. Some physical defect risks only appear weeks or months after manufacturing. In a solid polymer matrix, small particulate additives can slowly migrate upward and crystallize on the surface, a process known as blooming. To mitigate these delayed defects, formulators use accelerated aging protocol design. Applying simulated temperature and humidity spikes compresses years of environmental stress into a reliable, short-term testing window. Internal formulation defects are only half the battle. External vulnerabilities within the raw material supply chain pose an equal threat. A minor specification variation in a single raw material from a Tier 2 supplier can cause a catastrophic failure across an established product line. To defend against this, teams apply supplier variability and robustness engineering to design formulations capable of absorbing minor raw material fluctuations without failing. True engineering resilience is measured by a product's ability to maintain acceptable performance despite inevitable variations in time, temperature, and global supply chains. Achieving a perfectly functional, scalable product means nothing if it is legally barred from entering the target market. Decades of abandoned industrial waste and unchecked chemical disposal have led directly to today's era of stringent environmental pushback and regulation. Manufacturers face intense pressure to clear regulatory compliance and submissions, specifically navigating strict frameworks like EU REACH and FDA requirements. The industry-wide mandate for PFAS-free reformulation requires technical teams to strip out highly effective legacy chemicals and rebuild product performance without them. Beyond chemical bans, entire corporate structures must now align with global standards through strict ISO certification guidance, including ISO 9001 and 22301. There is an overarching mandate for sustainability and circular economy integration. R&D goals are shifting away from single-use performance toward end-of-life recyclability. Regulatory compliance cannot be treated as a final checkbox by the legal team. It must be engineered into the molecular architecture from day one, or the product will die in submission. Early energy demands were rudimentary. Today, emerging markets require hyper-specific, extreme performance from every material they consume. The rapid push for EV materials and energy solutions requires advanced polymers and thermal management materials that push the absolute limits of current chemistry. The sheer speed of this required innovation makes artificial intelligence applications mandatory. Predictive modeling and design of acceleration allow chemists to sort and rearrange molecular structures at a rate that can compress months of physical testing into hours of digital iteration. But utilizing generative AI carries a permanent threat to intellectual property. Inputting proprietary data can inadvertently expose trade secrets to the open web and invalidate future patent claims. Surviving the next decade of chemical engineering requires R&D program design and management that fully embraces digital speed while heavily fortifying proprietary data control. A sprawling 30-hour theoretical course cannot solve a specific active supplier variability crisis currently unfolding on the plant floor. Providing professionals with an endless library of generic modules actively stalls R&D momentum. More content does not equal more value when a precise decision is needed today. OnlyTRAININGS bypasses the library model. We provide 90-minute sessions led by specialists with 30 years of experience in single, high-stakes domains, like SPUR polymers or catalyst optimization. Because the content is built around real industrial failures and scale-up gaps, it provides a structured logic that supports immediate troubleshooting. This shifts the focus from broad learning to the technical clarity needed to resolve an active bottleneck. This targeted methodology is why thousands of professionals and global industry leaders trust us to help them make more defensible technical decisions. Stop waiting and start applying. Equip your R&D leaders, formulators, and technical managers with the know-how they need at OnlyTRAININGS.com. When multivariable constraints threaten your product line, generic knowledge is not enough. You need the platform where expertise matters most.